This video will give you an introduction into regression analysis in SPSS. It is designed for beginners of SPSS with relevant knowledge of regression analysis. It will help you to solve the exercise that is given later. It will cover the following contents. You will learn how to perform a regression analysis in SPSS. You will learn how to describe the results found. You will learn how to identify a good model. And you will learn how to test if regression assumptions are met. Before you start with any estimation in SPSS, you will first need to formulate the research problem. This research problem formulation needs to be built on theoretical assumptions or on research hypotheses. So basically the idea of a research paper is that you read into different theoretical approaches, ideas, and then formulate research hypotheses that you would like to test using regression analysis. In reference to our example on international markets, I have here 3 examples of research hypotheses which I just came up with rather quick and dirty. To give you an example. First is countries with a high market potential will attract more inward foreign direct investment in the form of mergers and acquisitions. So the idea is that in a country or a market which has a high market potential, there will be more foreign direct investment flows in the form of mergers and acquisitions. And you remember that we had these variables in our dataset. Second research hypothesis is focused on innovative business environments and has the same idea that an innovative business environment will attract mergers and acquisitions into that country. Third research hypothesis is countries which are among the top emerging markets will attract more mergers and acquisitions. These research hypotheses are then transferred into a research model or a regression model. You remember from our dataset that we had a variable that was measuring mergers and acquisitions in US dollars or in millions of US dollars. And you can see here that this will be our dependent variable in a regression model. We will then use 3 variables to operationalize the different theoretical ideas here. So for example, a high market potential will be measured by GDP per capita. An innovative business environment will be measured by patent applications of residents in a country. And among the top emerging markets, we will use the top 20 emerging markets classification that was proposed by Bloomberg and that is available in our dataset. So basically we have a model where we have 1 dependent variable and 3 independent variables that try to explain the level of the variance of mergers and acquisitions in our model. Let us now jump into our SPSS data file to see how we can estimate this model in SPSS. I have now opened the file in SPSS, and that is exactly the file that we have been using so far, international markets. To perform a regression analysis, what we need to do is we need to click on Analyze, Regression, and then you can see here an option which is called Linear. We click on this and then a new menu will open up. This is the classical regression analysis menu that we can use. You can see here that you can choose a dependent variable. In our example, the idea was to measure mergers and acquisitions. We have 2 variables in our dataset that do so. One is looking at mergers and acquisitions measured in millions of US dollars. And one is looking at the number. I've decided to choose the one that is looking at millions of US dollars. We will click on that or mark it and put it here into the box, which is called dependent. Then you can see here we can choose 1 or more independent variables. And my idea was to test the market potential, and I decided to use GDP per capita. We'll choose that as the first independent variable. I wanted to test innovative business environment, and I wanted to measure innovativeness by using the patent applications. And I wanted to use the top 20 emerging markets. We remember that the top 20 emerging markets is a variable which is coded as 0 or 1. So either a country is among the top 20 or is not. So you can see immediately that it's also possible to use a 0, 1 variable as an independent variable in regression analysis. So now we have all the variables that we need in, and we've clicked on this button which is called Options. This is basically to check if the checkbox here, Include Constant in Equation, is checked. It is, so we will continue. The constant just is in, and that gives us an intercept later in the regression analysis, which will cover up or comprise all different effects that we do not yet have in our model, so that the regression line can start as an intercept, which is estimated as well. Let us click on OK. And then SPSS is performing the regression analysis. And you see again, I'll put that up, that SPSS is communicating with you using an output document. Let us step by step go through that output document that we see here. The first interesting thing that needs to be highlighted is the model summary. In the model summary, you can see something that is called R-square and adjusted R-square. The R-square is the coefficient of determination. It gives you an idea of how much of the variance in the dependent variable is explained by our independent variables. So in our example, around 21% or 20.6% of the variance in mergers and acquisitions are explained by our independent variables. The adjusted R-square corrects the normal R-square by looking at the number of independent variables and by the sample size. The adjusted R-square is used when you compare models of different size. So for example, if you compare a model which has 2 independent variables with 3 independent variables, you would compare the adjusted R-square and not the R-square value. But for now, we're just interested in one model. We would have a look at the R-square. The second thing that is interesting in our model is what is here on the table, which is called ANOVA. And you can see here an F value and a significance or a p-value. This is an F-test for the overall significance of the model. It tests the zero hypothesis that all independent variables have no impact on the dependent variables. So basically it tests or has the assumptions that all regression coefficients are 0. And the idea is, of course, that we would like to reject that hypothesis. And we can see from the value here in significance 0.001, which is below any of our thresholds, under 10%, under 5%, under 1%, that we can reject the hypothesis, so we can say our regression model is statistically significant. The next thing that we will be looking at is a table which is called coefficients. In the coefficients table, you have 2 different columns. One is called unstandardized coefficients and one is called standardized coefficients. If you want to use the regression model for example, a forecast, you will always use the unstandardized coefficients because these can be multiplied with the original values in the data set. So in our example, we have an unstandardized regression coefficient for GDP per capita of 0.498, we can say that mergers and acquisitions will increase on average by 0.498 millions of US dollars for each dollar increase of the GDP per capita. And the same interpretation goes for the other 2. You can also see that we have a constant, and we also checked whether the constant is included, which is the intercept of the regression line that you have in a graph. The standardized coefficients, also called beta coefficients, are also regression coefficients, but these are the regression coefficients that you gain in a model where all the variables are standardized before the regression is calculated. You remember that we talked about set scores or set transformation of values, and that is exactly what is happening here. The variables are set transformed, and on these set transformed variables, a regression is performed that gives you standardized coefficients. What is the advantage of a standardized coefficient? It simply is that is taking out different measurement levels. So for example, in our example, we had number of patent applications, GDP per capita in current US dollars, or being classified as a top 20 market or not. So we have very different units in which these variables are measured, and we cannot really compare the size of the coefficient here. We do not know if top 20 emerging market really is much more important just because it has a much higher value, because this higher value is a result of the units in which the variable was measured originally. And this is filtered out by a standardized coefficient. So the advantage is that you can immediately compare the sizes of these coefficients. And from this, you know that patent applications has the highest standardized coefficient and therefore has the strongest impact on mergers and acquisitions. GDP per capita has the second highest coefficient and therefore has the second strongest impact on mergers and acquisitions. Being among the top 20 is a value around 0, so it has almost no impact on mergers and acquisitions. Another thing that we will have a look at is the significance of the individual coefficients. So again, there is a hypothesis test performed, which tests whether this coefficient here is significantly different from 0. So the 0 hypothesis would be the standardized coefficient of the GDP per capita is 0. And our idea is, of course, that we would like to reject the hypothesis. This is done again using a t-test. So you have the t-value here, and you could manually compare that to a t-distribution, but we know already SPSS is doing that for us and is providing us here with a p-value. Again, what will we be doing? We will compare the levels here with our desired alpha, and then check, is the value below 10%, below 5%, or even below 1%. And we can see the GDP per capita and patent applications are both below even 1%. So these are two statistically significant independent variables that have a statistically significant impact on our dependent variable on the mergers and acquisitions. I have told you already that if you would like to compare two models in terms of their explanatory power, you would refer to the adjusted R-square and not to the R-square. Let us simulate this process. For our model that we tested or we estimated, we had an R-square of 0.206 and an adjusted R-square of 0.173. These values were gained in a model with 3 independent variables. Let us kick out one of the variables and see how these values change and how we can interpret that. We click on Analyze, Regression, Linear, and then we will kick out one of the variables, and I will kick out the top 20 emerging markets. And click on OK to reproduce the same output. For the new model, with only 2 variables in, we see that we have an R-square of 0.204 as compared to 0.206 for the first model. So we see the R-square is somewhat lower, but very, very slightly lower. This is maybe not so surprising because we have kicked out a variable that had almost no impact. But is this model truly poorer than the first model, or is it maybe even better in terms of explanatory power? This is something that we can find out by comparing the adjusted R-square. And we now have an adjusted R-square of 0.182, so of around 18%. The value for the first model was 0.173, so around 17%. And that actually means that our second model, which only involves 2 variables, has a better explanatory power than our first model. And this is exactly the way that you would interpret or compare the explanatory power of different models that you would like to test against each other. For our next testing purposes, I will nonetheless refer to our full model because that was the model that I wanted to test in terms of my theory. And I will just put the variable back in to go along the next steps with you. The next step that we would need to perform is we need to check the assumptions that underlie regression analysis. So we need to check if all our variables fulfill the requirements that are necessary to perform a good regression. The first thing that we can check is the level of multicollinearity. To do so, we click in this menu box on the option Statistics, and this opens up. And in this menu box on Statistics, we will check the box which is called collinearity diagnostics and continue. Let us click on OK and see what this delivers. The same output will be produced that we had already, except for that we have now one more information that was not in the last time, and that is called collinearity statistics. And the relevant numbers that we are interested in are delivered in this column here. It is delivering the variance inflation factors. The variance inflation factors measure whether there is collinearity between different variables in our dataset. So for example, it measures if GDP per capita and patent applications actually are measuring the same information or are covering the same information to our model, or bringing the same information to our model, are collinear. As soon as we have a variable that has a value which goes above the number of 5, we will have a problem of multicollinearity in our data. For our data set, we can see that for all variables we have a value of 1. So basically, there is no multicollinearity in the variables in our model. I mean, that is kind of the desirable outcome, but of course, when you will do your own analysis later, there might be a situation where you will face a situation of multicollinearity. So let us maybe try a model where we would assume that there might be some level of multicollinearity in, just to see what happens. In my example, I was measuring innovativeness by using patent applications. But there might be other variables in the dataset that could also serve as indicators for innovativeness. I remember that we had something about high technology exports. Let us try. I will click on Analyze, Regression, Linear, and I will add high technology exports to the regression model. And click on OK. SPSS is reproducing the whole output with a new variable. We see that our R-square is around 0.204, which is rather surprising. Could be higher. We have an adjusted R-square of 0.159, so that's even worse, already giving us an indication that something is not really contributing to the explanatory power of the model. And what you can see now, when you look into the collinearity statistics and the variance inflation factor, that the whole regression model is kind of disturbed. So it's not functioning properly. And we can see that there are two variables that show a very high variance inflation factor above the threshold value of 5. And that is patent applications and high technology exports. So the VIF is pointing us to a problem here that is in these two variables, and the problem that is that these variables are multicollinear, meaning that these variables are contributing redundant information to the model. In a situation like this, you would need to delete one of the variables from the model as a remedy. And we know already, if we delete high technology experts, we are back in a situation that is fine. I will just do it and kick it out again. And then you can also see that our typical assumptions on R-square and so forth are again back to normal. So the variance inflation factors are all fine, and we have no problem of multicollinearity with this model. So multicollinearity would be the first thing, or the first assumption that we would need to test when performing a regression analysis. There are actually 3 more tests that you can perform to check if regression assumptions are met. The 3 further tests all relate to the distribution of error terms. You remember when you saw the model at the very first slide of this video that we had an error term of the estimation. This error term basically bundles all the effects that are in the model, but that are not explicitly measured by our variables. The 3 tests of the error terms look first at, are these error terms randomly distributed? So is there no idea of non-constant variance or systematic pattern in the error terms. These tests relate to the test for non-constant variance and the Durbin-Watson test. The Durbin-Watson test itself is only used for time series data. So for example, if we would look at the same data over a couple of years, then we would perform a Durbin-Watson test, because the Durbin-Watson test is looking at how does the error from one year to another show a systematic pattern or not. Ideally, it should not. In our data set, we are not looking at time series data, so there would be no need to go for a Durbin-Watson test. What we would not need to test, nonetheless, is non-constant variance. So the idea is that the error terms show kind of a random pattern or random scatter plot, and that there's no systematic information that is bundled in the error term that is actually missing in our model. Because if we identify that there's a systematic pattern in the error term, we might assume that we have forgotten relevant variables to be included in the model. Let us see how we can test that. We click on Analyze, Regression, Linear. We are in the same box that we had already. Now we go to this option, which is called Plots. And when we open Plot, we can ask SPSS to provide us with a scatter plot of the error terms of the estimation. And it's kind of a cryptic thing, and I always have to look it up myself, what is what. But you can see here that there's something that is called Z-pret and Z-resid, and that is nothing else than the standardized residual. So residual is the error term, and the standardized predicted variable, or the standardized prediction of the dependent variable. And what we are interested in, we would like to see the distribution of the residual or the error term on the y-axis. And we will use our standardized predicted values on our horizontal axis. We can also then say we would like to see a histogram, and we might also be interested in having some normal probability plot. However, this has nothing to do with the normal curve that we have seen in the histogram so far when we have been using descriptives. It's a different plot. And I would rather recommend that we will look at some numbers later for looking at normal distribution. So I would just leave it here with a histogram. We click on Continue and click on OK. Again, the same output is reproduced, plus SPSS is adding another chart or some different other charts. Let us first concentrate on the scatter plot that is provided. The scatter plot can be used to now test for non-constant variance. So basically what we would love to see here is a scatter plot where all these error terms show a completely random distribution in the plot. So what I try to point here with my small mouse arrow is kind of a plot where we would see small little dots which are randomly distributed all over the graph. In our graph, however, we see some kind of a pattern or systematically different pattern of points depending on the axis here or on the distribution of values here. We can see kind of a line that goes like this, and we see a line which goes like this. So basically, we do not have constant variance of our error terms. What does it mean? Our model is not good enough. Basically, there is information that shows a systematic pattern at the error term, which is missing in our regression model. So it would be good to think of further variables that we might put into our model to make it better. In real life, the problem is that you cannot always produce a model that will be a remedy to this problem. So you might end up with a model where you still see a situation such as this, although you have all relevant variables that are available to you in the model. So it's not a situation where you should fall into deep desperation. It's just a situation where you just need to be open at the very end of your analysis and let the reader know that you had that situation and that the model still is not providing you with a perfect interpretation or a perfect comprehensive set of variables that are able to explain your dependent variable. It might also be that a different regression itself might be better. So for example, when you think of a situation where an independent variable has a nonlinear impact on a dependent variable, it might be better to use a nonlinear model. Now, we will not further comment on this here, but that could all be interpretations coming out of a scatter plot such as this. So let us summarize. We would have our variance inflation factors for multicollinearity, and we would have our scatter plot to check for non-constant variance. The third thing that we still have open, because we have ruled out our Durbin-Watson test, is the normal distribution of our error terms. For the normal distribution, we can see here that SPSS is providing a histogram, and in the histogram it's already providing this kind of normal curve, but not the normal probability plot. We didn't ask for that. So the question is, do we feel that this is an almost normal distribution of error terms? From my perspective, I have seen much worse charts than this one, so it's not looking that bad. But actually, for some cases, it's rather difficult to assess, and even this is, of course, not a perfect normal distribution. So we might be interested in having a value that is actually able to calculate a number, letting us know, do we have a problem of normal distribution of error terms or not? And I will show you how this works. To perform a quantitative test of normal distribution of our error terms, we first need to go back to our regression analysis menu. We go to Analyze, Regression, Linear, and then we can see that there is something that is called Save. We click on Save, and then a menu opens up where we can ask SPSS to save residuals of the estimation. And as we have so far looked at standardized residuals in our plot, we will also use standardized residuals here. You could also use unstandardized residuals, doesn't make so much of a difference. So we checked it here. I click on Continue and then on OK. It's reproducing the same regression model again. But what is interesting in this regression estimation right now is that our data set has been enriched by a new variable, namely the standardized residual that has been estimated in the last regression run. And the good thing is, you can see it also in the data view if you want to, it's given in the last column here, that we can now use this standardized residual for testing for normality. In order to do so, there's a different menu that we will be using, and there's a menu which you find under Analyze, Descriptive Statistics, and then under Explore. I will open this up, and under Explore we will just choose the variable for which we would like to perform a normality test. You can also, of course, perform these tests for any variables in your data set. We will now only concentrate on our standardized residual and put it into this box which is called Dependent List. I find the box headings a bit confusing, but it's just the upper box where we put in all the variables for which we would like to test for normality. Under this idea of options, you could specify whether SPSS should do the typical case-wise missing value or exclude the pairwise missing value. If SPSS is using cases, it will exclude all cases from the analysis for which we have missing values. So all of these cases where we have missing values will be excluded. That's absolutely fine if we have only one variable. If we do a test for normality where we have not only one variable, but a lot of different variables which we test simultaneously, and we go on with exclusive cases list-wise, and we would, for example, look at labor force with advanced education and our residual, it would exclude case number 2, 3, 4, 6, 7, 8, what is it here, 10, and so forth. So it will exclude all the cases where we would have at least one missing value. And this can be very disturbing because it reduces the data set a lot. So if you perform the test for more than one variable, I recommend that you exclude cases pairwise. That means that SPSS is only excluding the cases for the relevant variables for which the tests are performed. Now we can click on that. For our example, it doesn't make a difference because we only have one variable to be tested. But nonetheless, keep that in mind for future tests. If we click on plots, there's this checkbox that we need, which is called normality plots with tests. And I will check that. Continue and click on OK. And then there are a lot of different outcomes that are produced. And the most relevant one that we are interested in is called tests of normality. And you can see here that we have two kinds of tests, the Kolmogorov-Smirnov and the Shapiro-Wilk test, that both test for normality. So both of these tests test the zero hypothesis that the variable follows the normal distribution. So the idea usually is that we aim for not rejecting this hypothesis. That's kind of a different procedure that we had so far, because we are usually interested in rejecting the zero hypothesis. In that case, we would be interested in a normal distribution of errors, because that is the regression premise. So we are not interested in rejecting the hypothesis. When will we use which of the tests? We will use the Shapiro-Wilk test as soon as we have a data set which has below 50 cases. If we have 50 cases or more, we would use the Kolmogorov-Smirnov test. In our example, we have 78 residuals produced, so we have 78 cases. That is, we will look at the Kolmogorov-Smirnov test. And we see here our p-value will lead to rejecting the hypothesis, independent from the alpha level that we are choosing at 0.000, so it's even below 1%. So we need to reject the hypothesis that error terms are normally distributed. We do not have normally distributed error terms. What does it mean for our interpretations right now? We would need first to check, can we improve our model further to make this test of normality perform better or different? So are there any things or any remedies that we can follow? One of the things that might induce error terms to be non-normally distributed are skewed independent variables. We had that in the introduction to SPSS, that we looked at transformation procedures for skewed variables, so for left skewed or right skewed distribution of variables. So for example, we could use, for example, a logarithm on the independent variables and see, does this help in producing a result where we would have normally distributed error terms. Let us assume, and that is unfortunately also often the case, that this is not helping you in this test, and we still have non-normal distribution of error terms. What does that mean for our model? Non-normal distribution of error terms leads to problems in significance testing. So our significance values or significance testing are not as good as they should be. Often, if you have a sample size that is at least around 30 cases, these deviations from significance testing or the performance of the significance test is not so heavily affected. That means we have a problem here. We cannot be as sure about the values that we have as we could be if we would have normally distributed errors, but it will not change the whole world around. So in that case, we would just say we will choose a very low alpha level to make sure that our assumptions and interpretations are still right. So in a situation where we have more than 30 cases and non-normality of error terms, we might go for a 5% or 1% alpha level and not for a 10% alpha level, to just be sure that our interpretations make sense later. My simple example will stop here, as you now have all the tools that you need to perform a regression analysis, including the tests of all different assumptions. So basically, it would be now up to you to improve the model. Look at further independent variables, always in dialogue with theoretical foundations. Look at different strategies to find a remedy for the non-normal distribution of error terms, and so forth, until you have a model where you feel that you are satisfied enough with what you can present. And you will perform the analysis along the different menus that I just showed, and then you will start interpreting your results. How would you interpret the results of the regression analysis? I will just open up the regression once more, and then you would be asked to provide an interpretation of your results. Basically, in the interpretation, you would start with what you did. You would give the reader or the audience an idea of different models that you tested and why you think that this is the final best model that you can offer. You would then discuss explanatory power. You would discuss variance inflation factors and give the reader the idea that variance inflation factors do not show any problems. You would give the reader an idea about the constants or non-constants of variance in your error terms, and whether you have been able to solve the problems or whether you still have a problem in the data. You would then give the reader an idea of the normal distribution of error terms. Is it there? Is it not there? What did you do to solve it? That would be the first step. Then you would go into the more content-wise interpretations and then talk about what is the explanatory power of the final model. Is the overall model significant or not? Yes, it should be. Which of the independent variables show a significant impact on mergers and acquisitions? Which is the most important one of these variables? Which variable might not have an impact on mergers and acquisitions? So you basically summarize the findings that you generated by the regression analysis. In the next step, then you would refer back to the research hypothesis. We have outlined 3 different research hypotheses, and then you will give the reader an idea, are these hypotheses confirmed or not? So by means of your regression test, can you say that research hypothesis 1, that assumed that countries with a high market potential will attract more mergers and acquisitions, is that confirmed or not? And building on this analysis, you would say, yes, it is confirmed, because we have used GDP per capita as a measure for market potential, and we can see there's a statistically significant association between this variable and mergers and acquisition. Wonderful. Research hypothesis 1 confirmed, and so forth. So you would draw back to your hypothesis and discuss the findings against the research hypothesis. And then you might also outline some implications for the researcher. What can strategic managers do with your findings? What can country business makers or country policy makers do with your findings, and so forth? You would then conclude with future research recommendations and let the reader know what could someone else do better if he would have better data. What limitations did your approach have? What can future researchers do better than you did? And you will then outline exactly this. And that would be the full package of interpretation. Have fun with that. Now it's your turn. Try 1 or 2 first models yourself. You might use greenfield investment as a dependent variable and then see which 3 or 4 or 5 independent variables might be relevant, theoretically relevant in explaining the greenfield investments. Maybe these are different variables than the ones that I've been using. Think of, for example, how easy is it to start a new business because of a greenfield investment. You can also try, and that would be, of course, the optimum situation, with the variables that you selected beforehand and add it to the data set. Maybe you have collected some relevant variables on political environments, corruption, whatsoever. Try one of these variables and see if you find an interesting relationship between these independent variables and the greenfield investment. Compare different regression models against each other and identify your best quick and dirty model. I would go along with the R-square, adjusted R-square, and of course with the number of significant drivers in the model. And of course you need to check if all the regression assumptions are met or not, and maybe you need to develop a strategy how to find a remedy to solve any issues that might be there in violating regression assumptions. If you do that very, very quick and super fast, you might also optionally challenge my model and see if you can do better. Maybe you find further relevant variables that will make the explanation of mergers and acquisitions much better than my simple model with 3 independent variables was. Have fun in analyzing the data. I hope that this video will be helpful. If not, you might also have a look at the wonderful book by Sarstedt and Moi, who wrote a nice chapter on regression analysis, which also offers a step-by-step guide into SPSS. Have fun.